Hi guys, welcome back to Data Every Day. Today we're looking at a data set of investment bank customers where each record represents a transaction that a customer had with the investment bank, and at the end here we have to show all the columns. I'll just show the last column. At the end we have the type of the product or the type of the uh, investing program type. So this is essentially the type of product that the customer is buying. I'm going to try to predict it using the other features, and I'm also going to try to employ some feature engineering to give us a boost in performance by creating features based on the other features we have here. So let's hop into the notebook. I'm going to be using a logistic regression model just to keep it simple, and then NumPy and pandas for working with the data, and then the train test split function and standard scaler from sklearn for pre-processing. So let's go ahead and import all of these, and we'll load in the data using pandas.readcsv. You can grab the CSV file path over here and paste it in and take a look. Just boost this up a little. Alright, so here's our data. And you notice immediately we can't see all the columns because we have over 20. So I'm going to go into the console here and type pandas.setOption max columns none. And that will allow us to see all of the columns when I reload the data frame. Alright, so these features currently do not have descriptive names, so let's hop into the description where it actually tells us what they are. So these the features have actually been anonymized. So to protect the security of the customers, they give us a rough understanding of what the features are, but they don't tell us explicitly. So this BA1 through BA7, that's these ones. These are banking activity features, money equivalent for general activities on customers' bank account in the last year, i.e. sum of payments for loan return. So these are continuous features representing monetary amounts having something to do with the customer's account. So we'll know those are continuous, we just want to remember that. And then the PE1 through PE15 is the investing history. These are flag features, or in other words, binary features. So back in our notebook, you can see that's these ones. And they either have a value of, I believe, is that an L or an I, something I0 or I1. So this is essentially just a binary column taking either a 0 or a 1. So what we'd like to do with those is go in and just remove the I off so that the model understands it as a numeric binary feature. And then we have the IA1 through IA3 columns, which is investing activity, which are counts. So counts are numeric or continuous features, so these do not need any sort of encoding. These are good as they are. So based on that, the only one of these features that we need to deal with are the PE features. So all we have to do with these is go in and remove the I's from there. And then there's two more features at the beginning, SE1 and SE2. Let's take a look at that. SE1 is the age, and SE2 is the geographic location. And over here it says if the value is less than 18, it denotes opening the program for a child. And then G0 as one of the values here means that no location is available. So this here, SE2, the geographic location, is a categorical feature. In fact, it's going to be a nominal feature since there's no ordering between these values. They're all independent geographic locations. And then the SE1 is actually the age of the customer, so that's already encoded as we'd like. You can see that takes a normal distribution. So what we'd like to do is create a pre-processing function. So pre-processing, and I'm going to create a function called pre-process inputs. Whoops. Pre-process inputs. That's basically going to take in the data frame. It'll make a copy of the data frame, and for now all it's going to do is return the data frame. And so we'll add all our pre-processing steps into this function, and then we can see the results down here. So I'll call the processed version of data x, and we'll pass data into our pre-process input function and get the processed version. So here's x. Currently it's just a copy of data, but that's fine. Now we're going to go in and actually do our pre-processing. So let's get a little more information on the dataset with data.info. Now from here we can see if we have any missing values. You can see we have 4,734 total entries, and that is the number of non-nulls in every column. So that indicates no missing values. We can double check that by typing data.isNA, which will return a true-false matrix where true represents a missing value. So if we then sum that over both axes, .sum, that'll sum across and down and across, and that will give us the total number of missing values in the dataset, which is 0. So we have no missing values, and we can go on to encoding now. So like I said, the only encoding we have to do is to one-hot encode this geographical feature, and then to remove the eyes off of these ones, these PE features. So let's start with, I guess we can start with the PE features. We'll remove these non-numeric characters. Remove non-numeric characters in PE features. So we could reference each feature by name, but there's, I feel like, a better way to do that, which would be to make a list containing PE plus string of I, where I is a character in range from 1 to 16. So this won't include 16, this will be 1 through 15. And then you'll see it'll concatenate the string version of that I onto PE. So this is essentially a list of PE1 through PE15. And this just is a lot more compact than writing out each one of these hard coding. So we're now going to iterate through this list for each column in this list of columns. We're basically just going to take the column, and we're going to apply a function to it, a lambda function where x is a given value. And since all of these are encoded the same way, and we know we have no missing values, all we have to do is set x equal to x sub 1, which will reference the second character only. So essentially, this is chopping off the I, because it's setting I0 just to 0, or it's setting I1 just to 1. And then afterwards, I'd like to turn it into a string column. So, sorry, an integer column. So I'm going to cast it to numpy.int. Now we'll get back the data frame, we'll check that, and you can see they have been encoded properly. We no longer have those eyes, and now these are all integer columns. So the last thing to do for encoding is to get this SE working. So let's one-hot encode the SE2 column. To one-hot encode, we'd like to use this function pandas.getDummies, which takes in the column SE2, instead of df here it's x, and it's going to create a new column for each unique value in the original column. So it looks at SE2, it gets all these unique values, and then it constructs new columns out of them, where each vector for a given example is now a one-hot vector or a sparse vector, meaning it's all zeros and just a single one, the one denoting the original value of that example. So down here, you can see we have G29, G0, G0. So up here, for the first three examples, we have a 1 in the G29 column, and then a 1 and a 1 in the G0 column. So this is how I'd like to encode the feature. I'd like to just take all these columns here and just put them onto our dataset. And then we'll remove the original SE2 column once we've done that. So up here, one-hot encode. Let's call those dummies that we just made geodummies. That will use pandas.getDummies for df sub SE2. And then I want to concatenate them onto the side of our data frame. So I'm going to set the data frame equal to pandas.concat. And we're going to concatenate the original data frame and the new geodummies side by side, so axis 1. And then once we've concatenated them together, we no longer need the SE2 column, so I'm going to go ahead and drop that. df.drop SE2 from axis 1. Alright, now let's take a look. So here's our new data. You can see we have the original data set here. The SE2 column is gone, and now we have the whole SE2 column encoded as one-hot columns on the end. So we still have our investment type column, but it's okay to keep these as text labels. sklearn doesn't mind. There are some libraries that require you to convert them to integers, but for now, this will work. So now, since we've encoded our whole data set, everything is numeric, I'm now going to split it into x and y. So split df into x and y, where y is going to be what we're trying to predict, in this case the investment type column. So y will be df sub investment type, and then x is going to be all the rest of the data. So df.drop investment type from axis 1. And now, instead of returning df, I'm going to return x and y separately. So let's go get those back over here. Now if we look at x, x no longer has the investment type column over here, but now it is stored in y. So y is just the investment type column. So this is what we're trying to predict, and you'll see the indices will match up to the examples where we now have the feature data up here. And so I'll now make a train test split. So this is using the train test split function from sklearn. Train test split, passing in x and y, specifying a train size of 70%. And this automatically shuffles the data by default. So let's include a random state as well to ensure that the shuffle is always done in the same way. And now this will return 4 new sets of the data: xtrain, xtest, ytrain, and ytest. And now let's return all 4 of these instead of just x and y. So we'll return that, we'll get them back over here, and then let's take a look at xtrain. So xtrain should be exactly the same as x, except the indices have been shuffled around, and we're now looking at only 70% of the data. So xtest is just the remaining 30%. Then we have ytrain instead of just y. So this is, again, 70% of the data that matches up with these. And now we can scale the data. So right now, each column takes on a varying range of values. This takes values only between 0 and 1. Over here, we have values all the way up to 289,000 and so on. So I'd like to standardize each column so that they all take on the same range of values. So for this, I'm going to scale x with a standard scaler. So a standard scaler is a scaler that will basically give each column a mean of 0 and a variance of 1. So every column will have the same mean and variance. That will encourage most of the values to lie between -1 and 1 in a given column. So let's create the scaler. I'm going to use the standard scaler from sklearn. And we can fit this scaler to just the train set, because we sort of want to assume we only have access to the train set at the time of pre-processing. And then we'll transform both the train and test sets using this fit that we have to the train set. So scalar.transform. Here we're transforming xtrain, and down here we're transforming xtest. And I want to note these do return numpy arrays. So if I go and take a look at this, we can now no longer visualize it as a nice data frame. So let's go in and turn them back into data frames with pandas.dataframe. And since we are reconstructing it, we want to specify the column names again. So the column names will just be x.columns. Now we'll take a look. Here's our xtrain. So it's like it was before, but now all the columns have been scaled. We can verify this by typing or finding the mean of each column. You can see they're all extremely close to 0. And the variance of each column, they're all extremely close to 1. So it has been scaled, and now we can feed it into the model. Most models prefer that your data is scaled. It will improve performance dramatically. So let's start training. So I'm going to create the model. This is a logistic regression model from sklearn. And we're going to fit the model to the train set only, xtrain, ytrain. Then down here we'll get the accuracy, which we can get from model.score, evaluating on the test set only, and then printing out the accuracy value. Test accuracy, we can display it to 2 decimal places with the percent sign, and format that with acc times 100 since it's a percent. And you can see we have an accuracy of about 67.98%. So it's not too bad, but I'd like to see if we can improve it using some feature engineering. So feature engineering is sort of a broad term, but it describes basically we have some set of features already. Let's try to derive some new features based on the features we currently have, and this can improve the performance of the model, especially with a simple linear model like this. There are some patterns in the data here that maybe if we were using a more complex model, the model could figure out on its own. but it would be nicer and more easy on the model if we specified those explicitly. So for example, if we look back at the descriptions of these, we have an age column, and it also points out specifically that if the customer is less than 18 years old, it's a program for a child. And so maybe you might think, okay, let's make a child feature. So if the age for a given record is less than 18, we'll have an extra feature that denotes that that record is for a child. So let's do that up here before we make the split. We'll say engineer age features. And so to do this is not too hard. We're just going to take the original age column, which is SE1. Look up here. So here's the age column, SE1. So I'm going to take the column and I'm going to apply a function to it that's going to, for a given x, return 1 if x is less than 18, and otherwise it will return 0. So this will be a binary column that's consisting of only ones and zeros based on if a given age is less than 18. And then I'm going to, this should be SE1. And then I'm going to store the result in a new column called child. And now if we run this and take a look, at the end here we do have a child column. Now it has been scaled, but essentially this is zeros and ones in the child column. We can verify that if we just take xtrain sub child dot unique. You can see it only has two values. They have been scaled, but they represent 0 and 1 respectively. So that's interesting, and I'm trying to think of another one we could do with the age column. So I think maybe we could have a senior column. So take this same thing and just make a new one, but instead of child, it's going to be senior. And this will be the same, but instead of x is less than 18, it'll be x is greater than or equal to 65. So if someone is 65 or older, we'll denote them as a senior, and that may also help the model. So now if we look at this, you can see we have both a child and senior columns at the end that were generated from our original age column. So let's see how that affects the performance of the model. So let's down here. Okay, so let's just grab that, and I'll say with no feature engineering, that's our accuracy. So now let's see with feature engineering. Let's see what we get. And we have an increase of almost 2% accuracy. So you can see that by specifying that information that was technically already in the dataset, but by specifying it in a more explicit way, in a way that the linear model can easily pick up on, we did have a performance increase. So I'm going to try one more thing to see if we can get a boost, maybe get us into the 70% range. The next thing it's not so easy with this dataset because we have anonymized features. We're not really sure what all these features are. If you know specifically what a feature is, you can come up with a lot more creative features to engineer. But basically, we do know that these continuous range features, bank activity features, represent monetary values. So I was thinking maybe we could have like a low balance feature, or a low balance feature for each of these bank activities. So if there's a low value in a given column, then we can create a binary flag feature that's going to say 1 if it's low and 0 if it's not, and maybe see if that works. So down here we'll say engineer activity features. And to do this, I'd like to access the quantiles of the column. So if we take, actually let's do, I guess we'll do it with data, our original data. Data.describe. For each column, we can get a sense of the distribution of the values in that column. You can see we have the min, the max, and then the quartiles, right? The 25%, 25 percentile, 50 percentile, 75 percentile, and you can see the values for each one. Wow, for this one, wow, look at this. Most of them are zeros, and they occasionally have a really high value. So I'm not sure what these represent, but I want what I'm going to do is for each one of these, I'll get a new feature that says there is a low value in that column. So by low, I'm going to define low to mean under 25%, under 25 percentile. So these are the 25 percentiles, and in a given column, if we have under that amount, we will say it's low, and if it's over that amount, we'll say it's not low. And we can access this easily through the percentile function, actually quantile function. So we'll type in, we're going to, not data, actually data sub BA2. Let's use the BA2 for example. If we use quantile and type in 0.25, then it will, okay, let's do BA3 instead so you can see. Then it returns the 25.25 quantile value over here, which does turn out to be this one. So that's the same value here. And I guess we're ready now to actually implement that using this function. So over here, I'd like to do a similar thing to what I did up here with the PEs, but instead of actually typing out BA1 through BA7, I'm just going to create a list of BA plus string of I, where I, for I in range 1 to 8. So that's 1 through 7. And then we can say for each column in this list of columns, we're going to create a new column, which will be called low plus column. So it's just going to take BA1, it'll see low BA1, low BA2, low BA3, etc. And that column is just going to be the original column, but with this function applied that says x will go to 1 if x is less than df subcolumn dot quantile of 0.25. I'll say less than or equal to, and otherwise it'll go to 0. So here is our function. This will send x. It'll send x to 1 if this condition is satisfied, and otherwise it'll send it to 0 for a given x in our original column. And we're doing that for every single column in the BAs. So we'll end up with 8 new features, 1 for each of these features. Alright, let's check that out. And that might just take a moment, so it's going to calculate the quantile for each column. The quantile function, if you think about it, is actually going through every value and then finding the distribution and then calculating. So it might just take a moment. So I'll resume the video when it's done. Alright, finished. And at the end here, you can see, I'll wait, all the way at the end here, you can see we have these low values. They have been scaled, but they contain zeros and ones based on the original values of these. So let's see how that works. So I'm going to grab this, and I'm going to say with age features, and then we're going to try it one more time now with the activity features added as well. And we end up with 71.15%. So we were able to get a performance increase up from 68% to 71%. So that's pretty decent. And it's a good demonstration of how feature engineering can be used to improve the performance of a model. So that will sum up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.